In this video, we're going to look at the coefficients of force on different surfaces of a cube. So we can just drag the CFX module into here and just right click on geometry and create a new design modeler geometry. Quite like to use design modeler for really simple geometries because it allows the hookup to the parametric workspace that I've shown in other videos. So I'm going to sketch my computational domain on the YZ plane. Just bias it slightly downstream so we've got that weight refinement, and I want to place the cube on the origin that you can see there, represented by the blue region. Going to put some approximate dimensions in. So I want the outlet to be about 10 meters downstream. We're going to have a 1 meter cube. The inlet only needs to be in the order of 6 meters. So we can bring that right down, and the width will need to be 3 on each side. And then once we've got that, we can extrude, put that in the order of 5 meters. We can have a look at our cube, see how it lies. And then we can expand these numbers out. Typically you want about a 5% blockage ratio. So if we just go back to that sketch and have a look at the numbers. So it's 3 by 3, 6 by 6, which is 36, and it's going to be a 1 meter cubed. So that's going to have an area of 1 meter. So it's about 3% blockage ratio. So we can allow that through. So next we want to sketch our cube, and we're going to sketch on the bottom face here. So we'll create a new sketch on the YZ plane. And this time just make sure it's coincident with that y-axis, because that will just hold the front face there. Don't have to be perfect sketching it out, because we can always correct it in a minute, like so. So add your dimensions. So you want it to be 1 meter wide. And then we're going to do a distance from the center to the arm and just make sure it's 0.5 meters to make sure it's centralized. And then sort that downstream length. And again, just make sure it's 1 meter as well. It's very close. Okay. So then to make that section out of the domain, I want to go back to here. I want to perform another extrude on that sketch. This time just make sure it's a cut rather than an add, and just make sure it's only 1 meter. And you can just right click on that and generate. Have a look at the preview if you want. Make sure what you're doing is correct. Doesn't matter if you need to do it 2 or 3 times to get it right, it's absolutely fine. And there you go, we've cut out that cube shape. So what I'm going to do slightly differently to what I've done before is actually bother to name these surfaces individually. So we can select from the inside, right click, name selection, call it front. I'm going to do front, back, top and sides. Actually, I'll select the sides together so they're one surface rather than two. Because we're doing a mean flow and it should be a symmetric case, there's no reason to have them selected differently. If you're doing instantaneous flow, you might want to choose that, but there's no real need here. And while we're doing this, I'm actually going to name the surfaces of the computational domain as well. You don't have to, there's no real need to. Just while we're in here, while we're doing the naming conventions. So that'll be inlet. I'm going to group these three together and call them slip walls because they're going to have a slip wall boundary condition. So I just generate that before I select these. There you go. And then we can name selection. Slip walls, generate, and then we'll do outlet. And finally ground. There you go, and that's our geometry and domain created. I'm just going to save that and then move on to the next stage. Okay, so just closing design modeler down and editing the mesh. Okay, so my case is loaded in meshing. I'm not going to spend long on the mesh here, I'm just going to refine it locally around the cube. Just going to do some sizing rather than some prism mesh generation because it's such a bluff body. So grabbing it, just selecting the inside faces. And right click mesh, insert and sizing. So you see there it's selected the 5 faces that stick out from the cube. I'm going to put these at 0.1 meters. This isn't really refined enough to properly resolve the flow here, or resolve the gradients I suppose if it's runs. But it'll give us something to analyse later. So when you're happy, just right click and mesh. If you'll have a look at some of the other videos from the channel, there are weight refinement boxes that are performed, so they might be helpful as well. You can see from the inside it's a relatively coarse mesh. We just want this to solve really quickly. And if we view from the top, we can perform a little cut plane. Perform a little section plane right down the centre. That will split and then, there you go, there's our box there. Cool, yeah, as you can see, really not refined enough, but gives us something to work with for now. Okay, and then when you're happy, you can hit save and move on to setting up the boundary conditions in CFX. Just make sure you click update and then the information will be passed to the setup process. Then we can go through the solution and post-pro. And right click, open up setup. And here we are. We've got our case brought in to CFX pre. So we're going to start by right clicking and creating some boundaries. So I'm going to start with the boundaries of the computational domain first. So we've got that lovely convention where if you type the same name, it pulls in the correct boundary type. Just going to select an arbitrary 5 meters per second wind for now. We're going to do our slip walls. So we're going to boundary details to specify that it's free slip. I'm going to select an opening for the outlet, but by default it pulls in outlet. Just select opening and pressure and direction 0 pascals. We'll select our ground plane. This time we do actually want that to be a no slip wall, so it's going to be slowing the flow down at that surface. Cool. So that'll give us a nice zero velocity condition there. And next we want to start looking at the cube, so just put in the names that we created. So that one's going to be just a wall, as are the others. So top, sides, and then the final face that hasn't actually been given a name, you can just rename that. So that's our back face. Again, that's taken as a wall. No slip wall, smooth wall. Cool. Let's just run through these, make sure we're happy. So we've got back, front, ground, inlet, outlet, sides, slip wall, and the top. Okay. So we can double click on default domain and make any changes here that we want. So things we might want to do is add some heat transfer, and I'll do that in another video. We'll use the same domain and case, and we'll do some thermal work. In this case, by default, it's got K-Omega SST at the turbulence model. I'm going to leave that, and we don't really need to do any initialization. It's not a complex case. It's got a nice, simple, low cell count mesh. We might want to look at solver control. So I'm just going to pull that local timescale factor down to 0.3. Just force convergence slightly. I'm not going to get it in this number of iterations, but again, it's just something to be looking at. Okay, so once you're finished with the setup process, we can just save and close, and then we'll give this a run. So you don't actually need to open up Solver Manager except for to specify dual precision, and if you have any local parallel options. I don't actually know what I've got in this PC, so I'm just going to run it on a single core. Such a small case, there's no point parallelizing. So just going to hit start run and we'll watch the residuals come up. So while a longer case might be running, you could, for example, hit plot monitor at the top and watch the forces. So you can watch the pressure forces in X at the front and the back. And you can see they're somewhat converging to a stationary value. Again, it's hard to really tell with the axes being, 50 times higher than these actual values. Okay, so that's nearly converged. You can actually change the range on this here. Actually, I'll show you what we're here. So it's 10 and 0. There you go. So you can actually see when you look closer, they are somewhat diverging, but maybe that's going to level off around there. We'll have a look at the force coefficients and see where they come out. So shut that off. Refresh. And let's have a look at some results. Okay, so we'll start off with just having a quick look at the flow. I'm just going to pull this wireframe away because it never looks particularly nice. We can turn on our ground and our cube. Okay, so I'm going to start by just creating a streamline set. It's going to be 3D streamlines, and we want to start from our cube. So to specify all those surfaces, you see it's highlighted really well there. We want quite a lot of seed points because a lot of them are going to die very close to the surface just because of the low velocity region and kind of reattachment, which will make it stagnate on surfaces and disappear. So you normally need to do a little bit of playing with streamlines. You see there, some of them have just died, and it's just a function of A, the kind of flow physics there, but also B, the really high cell size. But you can see that kind of recirculation region. If you seeded them upstream, hopefully you'd see kind of horseshoe vortex formation around the front there, but that's good enough for us now. I'm just going to apply pressure to one of the faces or one of the sets of faces. So just double click on, for example, sides here, have pressure, have it set to user specified, so maybe plus 10 pascals, minus 10 pascals. Okay. So nothing special, just shows you where you've got that negative pressure region kind of correlates with that separation region. And when you get reattachment, you get kind of pressures approaching neutral. Right, so the whole purpose of this tutorial was to have a little look at creating some force coefficients. So we can go to expressions at the top here, right click new, CD front. So if we go functions, force in the X direction, you could really for this do force norm in the X direction. I don't think it's going to show any difference. This will just take into account shear and pressure forces rather than just pressure. Sorry, excuse me. There you go. So we want it at the front. So we've got a front region there. So that's just the force, but what we wanted the CD. So in order to convert it from a force to a CD, we want to divide by half times rho, which we know to be 1.185 kilograms per meter cubed. That's the default at the current temperature in CFX. Half rho, so we need U squared. So what we can do, rather than just punching in a number, we can actually do like an area average. We'll put in the variable we want. this case it's going to be velocity in the U. And then where do we want it? We want it at the inlet. Excuse me, there you go. At the inlet. And then that's going to be times an area. So in that case, that's going to be 1 meter squared, because we had 1 by 1 by 1 for the volume of the cube. Cool, let's just look again, make sure that makes sense. So force is half rho velocity squared at the inlet and times A. So we've got a mistake here somewhere, so we just need to have a quick look where that's come from. I suspect that's my lack of closing brackets. There you go. Ooh. You see, there's a mistake here. So it's I only put the velocity, I haven't actually squared the velocity. So we're getting a meter squared left over. That's fine, we can just run that through the squared. And there you go. We've got a force coefficient, well, drag coefficient of 0.62 on the front face. And then running that back. CD back. Just change that to back, and then we'll get the back coefficient. There you go. So you see it's about 50% of the front. We could also do things like look at lift coefficient on the top of the cube. I can't remember what that would be from memory, right? It's about 0.1 or 0.3. But yeah, that's just a little demonstration how to create these force coefficients in CFD Post. If you have any videos that you'd like me to create, any tutorials you'd like me to go through, just put in a comment and I'll put it on my list for the next couple of weeks.